Good afternoon, dear colleagues, chairman. Today I will talk about chemical characterization of Dutch fine recycled concrete aggregates. You will have opportunity to see what are the current numbers in the Netherlands, what types of materials we have used in order to represent a recycling market in the Netherlands. Then which materials and methods were used for the study, what corrections to sampling is needed, some results, and of course conclusions. So in the Netherlands on the yearly basis, we produce around 33 million tons or 15 billion cubic meters of concrete, and for this amount, around 28 million tons of fine and coarse natural aggregates are used. They come mainly from the rivers, Rhine and Maas, and in the past we have used sea sand and gravel, but nowadays rarely. Numbers regarding the recycled concrete aggregates. So we produce around 12 million tons per year, and this is still not enough, neither used all in concrete structure applications. Of these 12 million tons, coarse and fine make 7 and 5 million tons, and they're mainly used for the constructions of the road bases. However, they, at least fine recycled concrete aggregates, have never been used for the concrete structures. So with this research, we want to change that state. What we in this study are aiming for is to find the quality parameters or indicators for the fine recycled concrete aggregates, so that we can efficiently use them in the concrete mix design, because there are many challenges in the literature and also in the practice when we regard the use of fine recycled concrete aggregates in new concrete. So the whole story goes about reduce the primary materials, don't use recycled concrete aggregates for making road bases, but actually turn it back to the new concrete structures. This is an example of how different types of fine recycled concrete aggregates are piled up at one of our partner recycling platform. So you can see already here by the color that there are different types of origins of these fine recycled concrete aggregates. In this research, we have used three streams of fine recycled concrete aggregates, and the locations were at east and in the central part, or let's say south part of the Netherlands. On the east, for instance, AWG Recycling Haaien, which is a down one, is importing the recycled aggregates from Germany. That information is very important to know for the Netherlands market, because we are not using only ours, we are actually having lack of, let's say, recycled or let's say demolished concrete structures. So with this, we hope that we have, let's say, a representative picture of the material used or recycled material produced in the Netherlands. The input material, as I said, the origin is not known. What we do know is that for these three recyclers, we know the recycling techniques. So they are also different between them. Storage is also different. One of them is not storing material at all, but is actually delivering at demand, while other two, C and D, are keeping materials in outdoor for a while. I have used these three batches to test or characterize material for all these properties listed here, and finally to select the quality indicators that are key, actually quality indicators, to be carefully considered in the concrete mix design. Here, I will only present the chemical part of the characterization. The rest you can find in the paper, which I shown in the previous page. So we have three sources of recycled material, and A is a river sand. You can already see by the color the first actually row of the materials, and different fractions of these materials. Since it's very hard to basically make a characterization of each of these fractions, I have decided to split this, or let's say to merge these fractions in two and start characterization from two of them, O2O25 and O225 to 4, and compare their properties to the total fraction O2 millimeter. The methods that were used were basically the first line of quality control is just the visual contamination, and then the chemical analysis, which are considering acid soluble chlorides and water soluble sulfates, as we are always regarding these as the major contaminants in the concrete in the environment, and of course to test the potential reactivity of the refined recycled concrete aggregates, which is very important because many studies have reported, and also practical experiences are, that in these fine recycled concrete aggregates there is a potential to replace partially cement or to be used as a filler, not only as a sand. We will see if this is the case for the studied Dutch recycled concrete aggregate. So here you can see the contaminants that we found in the different groups or streams in which are studied. So steel, rubber, glass, wood, nylon, dry grass, and so on. However, these contaminants were up to 5%, and this is like not that worrying, considering that this material is not washed at all at the recycling plant. Further, I would like to give you an illustration actually how this material looks on a micro level. So for two different groups of particles, one is 2 to 4 millimeter and one is below 2 millimeter. So what we can see here is that the river sand has a perfect shaped particles, which are mainly white. In recycled concrete aggregates particles, we can see something, let's say, which is actually cement paste. Cement paste in recycled sand is actually uttered around these primary aggregates, sand particles in concrete. Then you can see two particles, and they have absolutely different qualities. So one is very dense, let's say with the cement paste around, and another one is with a very porous cement paste, and it's of course consequently actually it comes from probably low quality concrete. On the other picture, on the right picture, for the smaller particle size, you can see that there are particles like where a lot of cement paste is, and the particles which are consist only of the quartz, or let's say just mineral particles. So now you can see basically the main difference here is the cement paste compared to the river sand. And of course, this material is mainly crushed, so the shape is also very important. In terms of chemical analysis, here we studied chlorides and sulfates according to the standard. However, the amount of material that is given by the standard is not followed, because we cannot use, as we are used to do with checking the chloride content from chloride contaminated concrete, because we need a larger sample weight in order to really have a representative values of, let's say, contaminants, chloride and sulfate, since they are also on a very low amount anyway in non-contaminated concrete, or they are not at all there. So we studied acid soluble chloride ion content because this, even though it overestimates the chloride, it would overestimate the chloride content in concrete, it gives an additional margin of safety, and it should be used in calculations of the concrete mix design. While for the sulfates, we should use the water soluble sulfates, since the acid soluble sulfates are not that common for or the water soluble sulfates actually are main that should be checked for expensive basically reactions that could occur for concrete during the service life. And here is the table that gives the maximum values of water soluble sulfate content of recycled aggregates. Further, the results on our materials are, so you can see here for the river sand, the cement paste, the acid soluble chlorides, and water soluble sulfates. What we can see is that in 100% we have basically up to 30% of cement paste, and then there is less cement paste in a coarser fractions, so above 250 microns, and in the total. For the acid soluble chlorides, as you can see, it's basically more or less similar, and throughout the batches, even though they all come from different exposure classes and different concrete type. Then the water soluble sulfates, here is actually something different. Like here you can see that in the lower fractions, actually in a finer fraction, we have big concrete, so below 250 microns. We have more sulfates than actually in the coarser fractions, above 250 microns, so above 0.2. So here what we can see, it is good to use 0 to 4 millimeters as a total fraction as a replacement to sand, then to split and use fine fraction as a replacement. Then we also check the potential reactivity. So we did have 3 cases. So we measured the potential reactivity of adhesive sand, so where there is some moisture, and then of the recycled sand and water, and recycled sand and cement. What has been found is that there is no reactivity. Basically, there is a negligible reactivity, and that is documented in the paper, where you can read more about that. So compared to the cement paste, where we have a very characteristic peak for the formation of hydration products after 8 to 16 hours, the heat release for the recycled sand and water has been basically 0. And then when we plot cumulative heat on the scale of 288 hours, then we can see that compared to the cement paste, basically the reactivity, or let's say cumulative heat of any reaction that could happen between the water and the fines, and I mean the fines below 250 millimeter, is basically very, very low. So that of course asks for explanation, and explanation lies in the morphology and in the composition of the old cement paste. In the Netherlands, in the past, we used very coarse cement. And as you can see, here are clusters of, or let's say grapes of, are very familiar to all of us, cement clinkers. And they cannot, or these clinkers cannot, at least cannot react in the conditions that are studied in this study at this temperature at 20 Celsius degrees. And what can react is actually the cement hydration products, but only if they're thermally reactivated. So to conclude, the recycled sand that is studied in this study doesn't show any reactivity. And this is due to coarseness of the cement that is used in the past. I would now like to conclude on the study. So the quality of the recycled sand is strongly dependent on the origin, and the recycled sands are mainly made of the crystalline phases. So the details you can find in the paper, and notably there is quartz, and on average there is 22% of the cement paste. As I said, the reactivity was negligible, and this means that this recycled sand can be straightforward used as sand replacement in the new concrete, and from the aspect of contamination, it has a large potential for the use in new concrete mix designs. I would like to thank you for your attention, and I'm happy to answer any of your questions.